This video is a continuation of the process of balancing redox reactions. You should have already watched the video on balancing neutral state reactions, and today we're going to talk about a similar process, but a little bit more complex, balancing reactions under acidic conditions. As with all the videos, we're going to start with a recap of what redox reactions actually are. This is to make sure that the ideas are fresh in your mind. We're now going to introduce these guys, the balancing reduction oxidation reaction rules. We didn't need these for neutral reactions because they simply balance using the same rules we've already used for other reactions. Under acidic and basic conditions, however, we have a new set of criteria we have to deal with. We'll identify those rules and we'll use them later on. We'll then basically go into some examples that talk about the actual process for this. We'll start with a list of the learning objectives for the video itself. As with all these videos, we'll begin with a discussion of what redox reactions actually are as a refresher to make sure that the ideas are fresh in your mind. We'll then talk about balancing redox rules, and this is actually probably the most significant part of this video here. For neutral reactions, we didn't need a special set of rules because they balance under the same conditions that other chemical reactions do. In acidic and basic reactions, however, there's a new process going on, and we've identified a set of rules to help guide you through that process. This rule covers any type of redox reaction. We're going to focus primarily on balancing reactions under acidic conditions today, and then we'll wrap up with a list of a couple examples. Again, one that I'll walk through together with you, and another problem I expect you to work on your own. So as we said a couple times now, a redox reaction again is the transfer of electrons between atoms during the reaction. We always have an electron donor and an electron acceptor, and that defines what chemical is being oxidized and what chemical is being reduced. Balancing these, and this is where this is going to become more significant, again requires us to conserve everything. Just like always, we'll need to conserve the number of atoms in the reactants and products, but now we also need to conserve the number of electrons gained via reduction or lost via oxidation. So that's why this process is more complex. We're now balancing or keeping track of two groups of substances as opposed to just one. Before we just had to focus on atoms. And again, as always, we'll talk about the fact that these reactions do happen under three different types of main conditions. The reactions happen under neutral, which we've already discussed, and we talked about the fact that there's nothing going on here. Acidic conditions, which is the new topic for today, that's what we'll be discussing. And then the third and final video you can look at later is basic conditions. As always, on the pH scale, and that's what this is all referring to, pH of 7 denotes a neutral scenario. As we get below 7, we have increasingly acidic situations, which means we have excess H+ ions available, and we're going to use those H+ ions from the solvent as a tool to actually balance the reaction. In pH is greater than 7, that's when we're dealing with alkaline or base scenarios. Here's where we have excess OH ions available, and when we balance our reactions in basic conditions, we'll be taking advantage of those, just like we'll be taking advantage of the H+ today. So here's where things start to get a little more intense. We have now a list of 7 or 8 rules that are going to be used for balancing redox reactions. I think it is absolutely imperative that you have a copy of these rules out in front of you. At first, they're not necessarily going to make a whole lot of sense, but when we use them in actual balancing processes, I think you'll start to see how this all works together. If you want to write out these rules, you're certainly welcome to do that. It'll be on this slide and the next slide. There's also a printed version of these rules available at the bottom of the page. You can download that. Either have it in front of you on a screen and or print it out so that you have them handy to use. Let's go through the rules one at a time and talk about what's going to happen in each of them. In the first rule, your first job is to balance the chemical reaction except for the elements oxygen and hydrogen. We'll tackle those a little bit later. And this is just regular old chemical balancing, so anything you've normally done before still applies here. Once the balancing is done, the next thing you're going to do is assign oxidation numbers to all of the elements in your chemical reaction. We've already talked about a video that tells us how to do that. You need to make sure that you figure that out. You're going to then be asked to identify which element is being oxidized and which element is being reduced. That, again, has been covered in previous videos. If that seems uncertain to you, go back and check on those. In the previous video, we talked about this step, writing a reduction and oxidation half reactions. It's simply a matter of identifying what's being oxidized and reduced and writing them as separate reactions, showing electrons as either a reactant in the reduced case or electrons as a product in the oxidized case. Now, here's where things start to get a little interesting. Here's the new scenarios. These are the ones that are only true in acidic and basic. You're going to balance the half reactions for oxygen. Remember, we didn't do that before. We left that out. You're going to do that by adding H2O, and here's the oxygen we're interested, to the side of the reaction that is missing oxygen atoms. So to make up for the missing oxygen atoms that we don't have, you're going to add in H2Os, enough of them so that the oxygens on the left side of the reaction match the oxygens on the right. However, this also creates the problem that you've also introduced H's, and that's where our next step is. You're going to continue balancing those half reactions for H now by adding in H pluses to the side of the reaction that's missing the H's. By adding in a whole bunch of H2Os over here, that means we're going to add in a certain number of H pluses over here to get these to cancel out. Sometimes it's just a matter of getting the H pluses from the water to cancel out. Sometimes there are other H's in the reaction, and that requires the addition of more H pluses. Let's continue our rules. Rules 6, 7, 8, and 9. Rule number 6 only applies when you're dealing with basic solutions. I do actually think you should take a moment and either write it down or make sure that it's on your list, but we're not actually going to be referencing this rule today. So at this stage in the game, that brings us to rule 7. You should have already gotten your reactions balanced for hydrogens and oxygens as well as the other elements by adding in H pluses and O minuses. Now it's time to balance both half reactions for the number of electrons gained or lost. The number of electrons gained or lost must be equal to one another, and the way we do that is by multiplying half reactions by some sort of constant multiple. So for example, if one half reaction has 1 electron and the other half reaction has 2 electrons, we'll double everything in the 1 electron one so that eventually the number of electrons are the same. Once you've done that and you've got all the electrons balanced and all the atoms balanced, you're going to combine those half reactions back together. So that's the name of the game here. And then the last step is to take anything in the reaction that shows up on both sides, both as a reactant and a product, and we're going to cancel them out. The electrons will always cancel out. We don't need to show them in reaction, but we do need to use them to get them to be balanced. And then typically other things that cancel out are excess waters, excess H pluses, and excess OH minuses. You'll cancel all that stuff out, and then eventually you'll write a final reaction afterwards. So here's our first example of balancing under acidic conditions, and we're going to go through the steps one at a time. We'll do this one together, and again, have that sheet in front of you with the steps so you're very clear as to what's actually going on here. The first thing it's going to want us to do is balance the reaction for elements other than hydrogen and oxygen, and I think the only thing we have to do here is put in a 2 here to get our chromiums to match. The nitrogens already match, and again, we ignore the oxygens. Once that's done, we want to assign oxidation states, so I'm going to do that really quickly. Now that we have our oxidation numbers assigned, we can clearly see what's being oxidized and being reduced. Chromium is going from the +6 state to the +3 state. That is reduction. Nitrogen is going +3 to +5. It's increasing in charge. That is oxidation. So we're going to write our reduction and oxidation half reactions. Now, I said this before in the last video, and I'll say it again. Make yourself lots of space. We have a bunch of steps here. And actually, leave yourself lots of space here as well because we're going to be adding things in. So again, the oxidation reaction happens with the nitrogen. We're increasing in charge. So that means the NO2 with a -1 charge is reacting to form NO3 with a -1 charge. And in the process, the nitrogen went from +3 to +5, which meant that it's giving off 2 electrons. Remember, in oxidation reactions, the electrons are always the product. The reduction reaction happens with a chromium. That is the Cr2O7 with a -2 charge. That's going from +6 to +3. We're actually going to be adding in 6 electrons here because there are 2 chromium atoms going from +6 to +3. Each one of them is gaining 3 electrons. Those 6 electrons then are going to turn into the 2 Cr+3 ions that we have. So we've now done our first couple of steps, writing the actual half reactions. The next step is where we actually do the stuff that's unique to acids and bases. You'll notice that these reactions are not balanced for oxygens, just for the nitrogen atoms. So for example, over here we have 2 oxygens, and on this side of the reaction we have 3 oxygens. The way we fix that is by adding in another oxygen in the form of H2O. Now we have 2 oxygens here plus this one to be the 3. But the next step then says once we add in the O's, we also have to balance 4 hydrogens. That means we have to place 2, not an H down, 2 down here. That means we add in 2 H pluses over here to balance out the 2 hydrogens that we had to add in for the water. Let's repeat the process down here. In this scenario, we're actually going to need 7 waters, 7 H2Os, because we have the 7 oxygens here to balance out, which means we're going to be adding in 14 H pluses on this side to make sure that those balance out as well. Now we've got this balance for all the elements in this reaction, and we've got a balance for all the elements in this reaction. That brings us on to step number 7, I believe now, where we're going to skip 6 because that only deals with basic conditions, and that's to get the number of electrons to be the same. Well, in this case, they're not, and it looks like if we take this whole entire reaction and triple it, that'll keep the balancing intact, but it'll also get us from 2 electrons to 6 electrons, and I do recommend taking the time to write the new reaction out. We're going to get 3 H2O plus 3 NO2 minus reacts to make 3NO3 minus plus 6 electrons plus 6 H pluses. And if you want, take some time, cross out the old version of the reaction so we don't accidentally use it later on. So that brings us to our last couple of steps. The last couple of steps are first to combine this into one line. Typically these do end up being very long like this, but it really was just a matter of taking all of the chemicals on this side of the reaction and combining it with all of the chemicals on this side of the reaction. And then we want to go through this thing and cancel out stuff that shows up on both sides. The first thing that always cancels out is the number of electrons. Remember, we made steps to make sure that these electrons would cancel out and that they were conserved. We can also see that we have 14 H pluses over here and 6 H pluses over here. I believe that leaves us with 8 H pluses left over. We can also see that the 7 H2Os here are going to cancel to become 4 because we're going to cancel out 3 H2Os from this side. And what's left now is the chemicals that are different and unique on the reactants and product side, and we can write just those as our final reaction. And what we now have is the final balanced redox reaction under acidic conditions for this dichromate ion reacting with the nitrite. And this is again what we're looking for. So what I hope you realize from this is it's a lot of steps, there's a lot of things going on, but at the end of the day, it's really just a matter of walking through those 9 steps that we outlined. And if you're willing to take those one at a time and take your time, you'll actually find that this process is not nearly as daunting as it might seem. So here's a second example. I'm going to leave this one for you to try, but you want to basically, again, go through the steps one at a time, all the way steps 1 through 9, and see if you can't come up with what the balanced version of this reaction looks like. So after a whole lot of steps, we can see here at the bottom that we have our answer. The reaction in some senses was a little easier than the last one. We didn't have to do any work with the oxidation half reaction. The reduction half reaction did require the addition of 4 water molecules, which required 8 H pluses, and then the other thing that was tricky is getting them to agree was difficult because we had numbers that didn't agree, 2 and 5. The common denominator that they all had was 10, so I multiplied this reaction by 5, this reaction by 2, rewrote everything, combined them into one line, canceled things out, and this ends up being our final results. If you didn't get this, that's not the end of the world. These are very difficult problems to do, and we'll clearly be spending time in class practicing these, as well as you practicing them on their own. And that's really what it boils down to. The more of these you work on, the easier and easier they're going to become. So here we have our list of things you should be able to do at this point. You'll notice it's extremely similar to the list we had before. The only thing we're really adding in here is being able to balance the redox reactions now in acidic conditions, and we do that via the addition of H plus and H2O molecules in order to be able to get our atoms to balance at the same time that we have our electrons to balance.